Hi friends, welcome to my another video. This is part third video in the series of variable frequency drive. In last two video, we discussed about the different speed control method of induction motor. We discussed about the three different method for changing the speed of the induction motor. First method which we discuss is the changing in the applied voltage method. And also we discuss about the drawback of this method. Then we discuss about the changing of the number of stator pole method, and we also discuss the limitation of this method. Then we discuss about the changing in the applied frequency method and what are the consequences of changing of the supply frequency method. Then lastly, in part 2 video, we discuss about the constant voltage frequency ratio method, which is the working operation or working principle of the variable frequency drive. So far we discussed about the different method of speed control of induction motor and the drawback of each method or the limitation of each method. Lastly, we discuss about the constant variable frequency method, which is the most efficient method among all previous method and which is the working operation of variable frequency drive. In this video, we will try to cover the different components of the variable frequency drive and how the variable frequency drive regulating the speed of the motor by changing the supply frequency and voltage at a time. So let's start this video. Variable frequency drive is acting like a magical box. When we are giving power supply to the motor through VFD, then VFD regulating the voltage and frequency of the power supply in order to regulate the speed of the motor. When motor need to be run in full speed, then the VFD giving same frequency and voltage which power supply have. And when we need to rotate the motor with lesser speed, then the VFD changing the magnitude of the voltage and the frequency of the power supply at the same time. But let us understand how the variable frequency drive changing the voltage and frequency of the power supply as per the requirement. In order to understand this one, we have to understand the different component of the variable frequency drive. Variable frequency drive have three main components. First one is input converter, second one is DC bus, and the third one is output inverter. The input converter section of the variable frequency drive taking three-phase AC supply and changing this three-phase AC supply into the pulsating DC supply. This pulsating DC supply will convert into the steady DC supply by using the DC bus. In DC bus, the ripple of the DC supply get filtered and getting a steady DC supply. The output inverter section converting again this DC supply, steady DC supply, into the required AC supply. What does it mean by required AC supply? Meaning with the required voltage and required frequency, so we can control the motor on our desired speed. So we will discuss one by one each section of the variable frequency drive. First we will discuss in deep about the input converter section, then we will discuss about the DC link, and then finally we will discuss about the output inverter. I gave you an idea how the variable frequency drive works. It is changing the AC supply into pulsating DC supply, then pulsating DC supply to the steady DC supply, and again this DC steady supply changing to the required AC supply with the required voltage magnitude and the required frequency in order to control the speed of the motor. The input converter is nothing but the combination of diode, and it is acting like a rectifier, controlled rectifier. As we know that the diode, like a PN junction diode, is acting like a closed switch when the power supply is in positive direction, and the diode is acting like a open switch when the power supply is in negative cycle. So when the power supply is supplied to the diode, then it will chop the negative cycle of the voltage and allow only the positive cycle of the power supply. So we can say that there is only a pulsating DC after supplying AC supply to the diode, as the diode is only allowing the positive cycle of the power supply. So we can say that the diode is changing AC supply into the pulsating DC supply. Here in this photo, you can see that these are the diodes, and the combination of these diodes are called control rectifier. There is a 3 phases, so there is a 6 diodes in order to chop the negative cycle of each phase and to have the pulsating DC supply. Hope you understood the working operation of input inverter. As we discussed, when we are giving the 3-phase power supply to the input converter of VFD, then these diodes chopping the negative cycle of the 3-phase power supply and giving a rippled DC supply, as it is chopping the negative cycle of the power supply. Now let us understand how this rippled DC supply is changing into the steady DC supply by using of DC link. DC link is a combination of inductor and capacitor. When the pulsating DC supply is passing through the DC bus, which is the combination of inductor and capacitor, then it's convert the pulsating DC into the steady DC. Now let us analyze how this DC bus converting the pulsating DC into the steady DC. For that, I will take a simple rectifier circuit with the capacitor filter. If you will understand this concept, then you can understand this concept also. Here I took a rectified output, which is nothing but a pulsating DC supply. This we got after passing this through the rectifier. Now the voltage here across the load is a pulsating DC. In this section, we will try to learn how this pulsating DC is converting into steady DC. This is our motto. So what we will do, we will understand what this capacitor is doing, which we are connected parallelly with the load. Suppose there is no capacitor as of now. We given this pulsating DC supply to the load, then the voltage across the load will start increasing from 0 volt to 100 volt to 200 volt to 300 volt, and after that it will again decreasing to 200 volt to 100 volt to 0 volt, and again it is increasing. When there is no capacitor, means the voltage across the load will be the pulsating DC. Now as we connected the capacitor across the load parallel to the load, now let us see what the capacitor is doing and what benefit we are getting by connecting this capacitor as a filter parallel to the load. Suppose in the first cycle, the voltage here will increase from 0 volt to 100 volt to 200 volt to 300 volt. So the voltage here increasing from 0 to 100 to 200 to 300, and same the voltage across the load also increasing from 0 to 100 to 200 to 300. Now when the voltage reach till 300, then the capacitor get charged and it will have a voltage of 300. Of course the load also will have the same voltage 300. As the supply voltage reaches to its peak value, then the capacitor also get charged and the voltage across the capacitor become 300 volt. But now the supply voltage will decrease from its peak value, that is from 300 to the lower value, but the capacitor is fully charged and it has a voltage of 300. Then the source voltage will become lesser than the capacitor voltage, and in this time the current will start flowing from the capacitor to the load, and in this time the capacitor start discharging from 300 to 290 to 280, and at the same time the source voltage is also decreasing. Let's say when the capacitor get discharged to 200 volt, then the supply voltage become more than the capacitor voltage. Then in this time the capacitor voltage is 200 and the supply voltage is greater than 200 volt. Then in this interval of time the capacitor will start charging itself and there will be no current flowing through the load by the capacitor. So the load voltage will follow the supply voltage. So what we observe here, that when the capacitor is discharging, then the load voltage is not going less than 200 volt, but when the capacitor is charging, then there is no current flowing and the load voltage following the supply voltage. and again at the 300 volt of the power supply, again the capacitor gets charged to 300 volt. And now whenever the supply voltage is decreasing, again the capacitor voltage become more than the supply voltage, and again the current will start flowing to the load. And in this time the load voltage will follow the capacitor voltage. But as at the 200 volt the capacitor voltage after discharging become less than the supply voltage, then the current which was flowing through the capacitor to the load will stop flowing, and the load will start following the supply voltage. In same way, every time this will repeat this cycle. So what we observe that without the capacitor, when we are giving pulsating DC, then the voltage across the load is also pulsating. But when we connected a capacitor as a filter across the load, then the voltage across the load become close to the steady DC. So in same way, the DC bus, which is the combination of capacitor and inductor, making the pulsating DC supply into the close steady DC supply. So what we learned so far, that when we are giving three-phase power supply to the VFD, then the input converter section, which is the rectifier section, also converting this AC supply into the pulsating DC supply. And when we supply this pulsating DC supply to the DC bus of the VFD, then it's converting the pulsating DC into the steady DC supply. Now let us understand what this output inverter doing and how it is converting the steady DC supply into the AC supply. The inverter section of the VFD is the combination of IGBT, insulated gate bipolar transistor. These are called IGBTs. The inverter section of the VFD using pulse width modulation technique in order to convert DC supply, steady DC supply, into the AC supply. Now let us understand how this combination of IGBT converting the steady DC supply into the AC supply by using pulse width modulation method. In order to understand this one, we have to understand a simple circuit. Here we use 4 switches, 1, 2, 3 and 4. Now we given a DC source to this AC load. Let us analyze how this DC source is appearing for the load as a AC source. We will supply the DC source through this battery, and we will keep this switch and this switch on, and this switch and this switch is in off condition. So what will happen? This is a positive charge and this is a negative charge of the terminal. Then the current will start flowing from here, reverse back to the source. So this point will be positive and this point will be negative for the load. Okay. Now let us take another case. This is positive terminal of the battery. This is negative terminal of the battery. In this time, we close these 2 switches and we open these 2 switches. Then the power supply will come like this to the load and it will go back again to the source. Then in this time, the positive terminal is opposite from the previous case for the load. Okay, for the source nothing is changing, but for the load, positive and negative terminals are changing. Let us assume that this battery is a 12 volt battery and I'm keeping S1 and S4 switch on, S2 and S3 switch off. Then the voltage across this load will be 12 volt. Okay, but in next time I am keeping S1 and S4 switch off and S2 and S3 switch on. Then again the voltage across the load will be 12 volt but in the opposite direction. Suppose if I will follow this sequence, if I will repeat this sequence 50 times in 1 second, then the load will experience 50 times positive 12 volt and 50 times negative 12 volts power supply. For the load it is like a AC supply, but for us we are giving this power supply to the load from pure DC source. I hope you understood this concept, that how we can change the polarity of the voltage for the source by operating the switches in different manner. Now we have to understand the other important thing. Let's say the same case, this case we are keeping these 2 switches S1 and S4 on and S2 and S3 off. then we will have it positive 12 volt. Okay, but for this operation I'm doing for 2 nanosecond. Okay, next time again I'm opening these two switches and again closing by without disturbing these two switches. I'm again opening and closing it, but this time I'm closing this switch for 2 nanosecond. So we will get a wider width of the voltage, means for more interval of time there will be voltage across the load. Next time again I will open it and I will keep the switch on till 3 nanosecond. Then for 3 nanosecond the voltage across the load will appear. Then the voltage width will be more thicker. In next time I will open the switch for 1 nanosecond and I keep the switch on for 4 nanosecond. Then the voltage across the load will be for 4 nanosecond. Okay, this is the time scale and this is the ampere or magnitude scale. Okay, so what we did so far, we are keeping on and off of the S1 and S4 without disturbing S2 and S3, but we are making it on and off for a different interval of time. Meaning one time we are keeping it on for 1 nanosecond and we hold the switch on for off for 1 nanosecond. Again we put it on for 2 nanosecond and again we keep it off for 1 nanosecond and again we keep it on for 3 nanosecond. Meaning we are keeping the switch on and off for different interval of time. Then we will get the waveform like this. Fifth time, when we are turning off the switch S1 and S4, then again we reduce the time for the switching on 3 nanosecond. Again in this time the voltage across the load will be only for the 3 nanosecond, which is lesser than the previous one. Then the width of the voltage will be lesser. Hope you understood this concept. The same concept will be valid for this phase. Now we want, by completing this cycle, to change the polarity of our voltage across the load. Then we will open S1 and S4 switches and we will keep on and off S2 and S3 switches. Then the voltage across the load will be negative side. The voltage across the load always be minus 12 volt. But when we are keeping the switch S1 and S2 on and off for different interval, then we will get a different widths of the voltage. Let's say this is for 1 nanosecond, this is for 2 nanosecond, this is for 3 nanosecond, this is for 4 nanosecond. Again this for 3 nanosecond, this for 2 nanosecond, and again this for 1 nanosecond. Again we will keep on this S1 and S4 switch and again we will repeat the procedure which we did in the previous case. Meaning we will not touch now S2 and S3 switches, and again we will turn on and off S1 and S4 terminal. Again we will get this form. Hope you understood this concept so far. We can control the voltage across the motor terminal by varying the duration of the IGBT on and off position. If the IGBT is on for longer duration, then the voltage across the motor terminal will be better. And if the IGBTs are on for a shorter duration, then the voltage across the terminal will be lower. You can imagine from this waveform also. Suppose this voltage is 12 volt and the time is only 1 nanosecond. And this voltage is also 12 volt, but the time for opening the IGBT is 2 nanosecond. This voltage is also 12 volt, but the time duration to on the IGBT is 3 nanosecond. And same way it is for 4 nanosecond, 3 nanosecond, 2 nanosecond and 1 nanosecond. So when we will try to get the average of this voltage, then we will find that when the duration for the IGBT on is less, we will get less voltage, and when the duration for the IGBT is more, then we will get the average voltage will be comparatively high. So by switching the IGBT time duration, we can control the voltage magnitude across the terminal of the voltage. Now how we will change the frequency? As I told you, if we will switch this circuit to this circuit and this circuit to this circuit very fast, then we will switch the positive and negative cycle, and the frequency is nothing but the cycles. If we want more frequency, then we will switch this circuit to this circuit very fast, and if we want less frequency, then we will keep this circuit operate for longer time and then we will switch to this circuit and we will keep this circuit to on and off or to operate for longer time. In this way we will control the frequency. Suppose in this time we will switch from this circuit to this circuit, then this waveform will be in the opposite direction and we can say that it is a one cycle. So if the number of cycle in one cycle will increase, then the frequency also will increase. So by switching from one circuit to another circuit, IGBT changing the frequency, and by keeping the IGBTs on and off duration, IGBT is changing the voltage magnitude across the motor. Let us say we give 430 volt 60 Hz power supply to a motor, then this IGBT changing the magnitude of the voltage to 380 and the frequency to 53 Hz. In this condition, when the voltage was 430 and the power frequency was 60 Hz, then the motor speed, synchronous speed is what? 120 F by P. If we will calculate, we will get the RPM 1800 RPM of the motor. Now as the IGBT changes the magnitude of the voltage and the frequency of the supplied voltage, now the synchronous speed of same motor will become how much? As the frequency goes down from 60 to 53, the synchronous speed of the motor become 1590. So by this method, the IGBT changing its switching time duration and its circuit in order to have control on the voltage magnitude and the frequency of the power supply. So the inverter section of the variable frequency drive, taking the steady DC supply as an input and changing into the pulse width modulated waveform by controlling the speed of switching of the IGBTs and the circuits which IGBTs are operating. By changing the duration of the on and off of the IGBT, it is changing the widths of the pulse width modulation, and by changing the IGBTs from this to this or from this to this, it is changing the frequency of the pure steady power supply. So here I talk in my discussion that it is keeping on and off in nanosecond, which is not possible if there is a mechanical switch. These switches are solid state switch, and thanks to electronic development that it is possible to make on and off the circuit in microsecond to picosecond. For the simple explanation, I replace all the IGBT by a simple switch in order to better understand. But in the IGBT, there is no any moving part. In some condition, the IGBTs allow the current, and in some situation, the IGBT will not allow the current. And that's why it is also called the solid state switch, as there is no any moving part inside the IGBT. I hope after watching part 1, part 2 and this final part 3 video, you clearly understand how the variable frequency drive is working. I hope you learned something new from this video and you find this video very informative. If you really like this video, then please give thumbs up and subscribe to my channel. We will meet in any other informative video. Till then, take care, keep learning, and bye-bye. Thank you so much.